Hi again and welcome to section 4 of this course. In this section, we will use a genetic algorithm to simulate how life could adapt to survive on randomly generated exoplanets. You will learn to generate planetary environments with unique gravity, atmosphere, and temperature. Then evolve genetic features such as radiation resistance and oxygen efficiency using selection, crossover, and mutation. By the end of this section, you will visualize how fitness improves over generation and build a compact exoplanet survival simulator, showing how evolution and AI can work together beyond Earth. Section 4. Exoplanetary Adaptation Simulation by Genetic Algorithm. Before we start, I have to explain some definitions. What do we mean by exoplanet adaptation? How living organisms might change or evolve to survive on planets outside our solar system is exoplanet adaptation. What is genetic algorithm? A computer method inspired by evolution that finds better solution through selection, crossover, and mutation. Genetic algorithm is explained in section 1 completely. Genetic algorithm have some parts which I'm going to explain a little bit. Population, a group of possible solutions or genetic profiles that compete to evolve over generations. What is generation? Generation, one full cycle of evolution where the population is evaluated, selected, crossed, and mutated. What is fitness function? A mathematical formula that measures how well each individual survive or perform in a given environment. The higher the fitness score, the better the adaptation. Now, selection is the process of choosing the best individual to pass their features to the next generation. Crossover is mixing genetic information from two parents to create new offsprings with combined traits or features. Mutation is a small random change in features that keep diversity and help discover better solutions. As I mentioned earlier, for more information about genetic algorithm, please refer to section 1. What is planetary environment? A set of natural conditions on a planet, such as gravity, temperature, radiation, and atmosphere. Here we have 5 main features for our planets, which we produce them randomly. Radiation resistance, bone density, oxygen efficiency, temperature adaptability, and stress resilience. Radiation resistance is the ability of organisms to withstand harmful cosmic or solar radiations. Bone density, a measure of bone strength, important for surviving on planets with a stronger or weaker gravity. Oxygen efficiency is how well an organism can use oxygen from the planet's atmosphere to survive. Temperature adaptability, the capacity to live and function across extreme hot or cold conditions. Stress resilience, the ability to handle long days, harsh climates, or unpredictable environments. Fitness convergence here is when evolution is stabilized and no major improvement occurs, showing adaptation is nearly completed. Here at right, we can see a random star and its planet, and some features of that planet like gravity, atmosphere conditions like oxygen, carbon dioxide, radiation level, and temperature range, plus day length. So basically, high gravity needs high bone density. Low oxygen needs high oxygen efficiency. Strong radiation needs high radiation resistance. Extreme temperature range needs high temperature adaptability. Longer stressful day cycles needs high stress resilience. Our objective function here, using genetic algorithm, is to find the genetic profile that produces the highest survival score under that planet's environment. The genetic profile value comes from randomly generated population in each simulation. For example, radiation resistance, higher is better when radiation level is high. Bone density, ideal when it matches the planet's gravity. Too low is weak, too high is wasteful. Oxygen efficiency, good if it matches available O2 or oxygen in the atmosphere in that planet. Temperature adaptability, good when average temperature approximately equal to adaptability range. Stress resilience, better for longer extreme day lengths. In the simulation, the results would be something like the red text here, which we have 5 parameters, 1, 2, 3, 4, and 5, which are radiation resistance, bone density, oxygen efficiency, temperature adaptability, and stress resilience. 5 means the higher mutated value, but it doesn't guarantee the best result or the best solution. Here, for example, 0.67, a little bit of mutation happened for radiation resistance. Or here, 4.54 for bone density, means a lot of mutation happened. Again, I will emphasize that the higher mutation level doesn't guarantee the best candidate solution or the best result. Also, we are not going to compare our values with Earth rules, as it is completely meaningless, because each time we are going to create a new environment with different environmental factors. That means our organism, our creature, has different trait or biological trait or features to survive. Also, for each feature of radiation fitness, gravity, oxygen, temperature, and stress, we consider different weights. So for the radiation and oxygen, we consider higher fitness, weight, as they are more important. For the temperature and gravity, we consider like 20%, and for the stress, we consider just 10%. So in general, why does this topic matters? Studying exoplanet adaptation helps us to understand how life could survive beyond Earth under different gravity, radiation, and atmosphere conditions. It reveals the biological limits and flexibility of life in extreme environments. This knowledge guides both astrobiology research and the search for potentially habitable worlds. Why is GA or genetic algorithm works better as a solver here in this context? Other simple search algorithm just try random combination blindly. A genetic algorithm or any other metaheuristics learn from each generation, which it keeps good solutions, mix them, and mutates slightly to explore better ones. Genetic algorithm can handle multiple conflicting traits or features like radiation, gravity, oxygen, and more, and all of them at once. It naturally works with biological concepts like adaptation and evolution matching the problem. Please note that any metaheuristic like PSO, Firefly algorithm, differential evolution are proper to be used here, but we use genetic algorithm as the subject was related to the biological matters. It is robust to randomness and can still find good solution even with noisy or changing planet conditions. This is an optional slide you can read by yourself. So it is going to compare our planet features and our bioorganism features and compare them together, which shows what a feature from the planet matches with what feature of the creature or the bioorganism living there. So if the gravity is higher, evolution favors denser bones for support, stronger stress resilience to handle physical strain, and efficient oxygen to use to sustain muscle under pressure, while temperature, adaptability, and radiation resistance remain vital for long-term survival. And more. For example, if oxygen is scarce, evolution rewards greater oxygen efficiency, but also higher stress resilience to endure hypoxia, enhanced temperature, adaptability since metabolism slows, denser bonds to conserve energy in movement, and radiation resistance to protect weakened cells. Now we are going to investigate a bad case and a good case in our simulation. As our simulation each time is going to generate random solutions, random candidate solutions, random planetary environment. Here we have a bad result. As you can see above, we have the name of the planet and the star, which will be generated automatically by the system. And also the best fitness after the simulation, which shows 0.3. Okay, the higher the best fitness, the better the adaptability of that organism or creature on that planet. Here we have 0.3. That means the fitness is low, is not close to 1. It is below half. That means this planet environment most probably is not habitable for that bioorganism or creature to live there. Okay, for the gravity here we have like 1/3 of the gravity of Earth, but as I mentioned, we are not going to compare it with Earth. We are going to compare it with the other features of that bioorganism, alien, creature, or whatever you want to call it, and also with the other features of the planet itself. So here we have like gravity, very low gravity. Even though the organism evolved high bone density, approximately equal to 5, such dense bones are inefficient here, energy wasted, reduced fitness. Now atmosphere of 6% oxygen, around like 7% oxygen, and carbon dioxide of 49%. That means a lot of carbon dioxide. So we are going to see, we are going to have very low oxygen and extremely high carbon dioxide. Although oxygen efficiency is approximately equal to 5, which helps, that means a lot of mutation happened, the toxic carbon dioxide level makes survival difficult. Also for the radiation, we have 477 or 479 millisievert per year, or MSV per year, which is extremely high. Radiation resistance approximately equal to 4.9, almost 5 is good, but it's still not enough to offset the danger. Also, we have the temperature in day and nights from minus 45 to 96 degrees Celsius or centigrade, which is extreme range. Temperature adaptability is approximately equal to 4.2, allow partial survival, but large swing still stress metabolism. Day length is 10 hours, around 11 hours, which short days cause frequent thermal and light shifts. Despite a strong stress resilient, near 5, the rapid cycle limits adaptation. Best genetic profile, which we achieved after the simulation for this case, is, as you can see, all of them near 5. That means very high feature values, indicating organism pushed to its limit just to survive. That means a lot of mutation happened. But our best fitness is around 0.3. Low survival potential, harsh radiation, low oxygen, and unstable condition makes this planet truly suitable for life. So as we can see from the results, it's doing everything it can to survive, but the planet is still too harsh, so the fitness remains low. So the species evolved as much as it could, but the planet is so hostile that even a maxed out organism cannot survive well. So it is not about having higher values close to 5 or lower. So in this case, the effort is over. The genetic algorithm has already reached the best possible solution under those limits. The low fitness isn't from poor optimization, it's from uninhabitable planets. Please note that each creature, one row in the population, begins with random abilities, random level of radiation resistance, bone density, oxygen efficiency, temperature adaptability, and stress resilience. Now we are going to investigate a good case which ends up to 0.8 fitness value. That means very high. Basically it is 0.88, almost 0.9. So we can see them a planet's name and a star name, which is going to generate it randomly as other features. So we have gravity of 1.3, which is slightly stronger than Earth. The evolved bone density of 4.5 is high, giving solid skeleton strength to function under heavier gravity. Also, for the atmosphere, we have 49% of oxygen and 43% of carbon dioxide. Very oxygen rich, but also high in CO2. The creature evolved oxygen efficiency equal to 5. That means a lot of mutation for that part. Radiation of 415 MSV per year, which seems low. The planet's dense atmosphere and high oxygen shield enough radiation that extreme resistance isn't required, which saves a lot of energy. Temperature of the day and night is spanned from minus 73 Celsius to 31. Large cold range. Temperature adaptability of 4.7 allow operation in both freezing and mild warm conditions. Day length is just around 6.6, close to 7 hours. Very short day-night cycle, stress resilience of 4.9, that means a lot of mutation for this part, ensures stable metabolism, despite rapid light and thermal shifts. This genetic profile approximately equal to 0.6, 4.5, 5, 4.7, and 4.9. As we can see, a lot of mutation happens except the first one. A balanced combination, strong bones, high oxygen use, broad temperature tolerance, and excellent stress control. So we achieve 0.88 fitness value for this planet and its bioorganism. And it is very good for survival. This environment, though harsh in radiation and cold, is largely habitable thanks to rich oxygen and short, manageable day cycles. So there are important notes about this simulation, about the whole experiment, and about the explained good and bad cases, which are, in this simulation, the initial random population matters a lot because it defines where the search starts in the trait space or in the feature space. If by chance the starting population already contain individuals with traits or features closer to the ideal combination for that planet, the GA will find a good solution faster and reach higher fitness. If the initial population starts far from those ideal regions, even after hundreds of generations, GA might get stuck in weaker areas or converge on local optima, leading to lower fitness results, even though the planet itself could support life. The planet's parameters like gravity, oxygen, radiation, temperature, day length must match the candidate's feature, bone density, oxygen efficiency, radiation resistance, and more for fitness to be high. And that is very important. So basically, the random features which are going to be generated for the planet and for the bioorganism in the beginning in this simulation is so important, but you can change it for your own and personalize it for any type of project you want. Now we are going to formulate the whole experiment or the simulation mathematically. So we have some input, some processing, and some output. For the input, the model begins by generating a random exoplanet environment defined by P, which has G, A, R, T, and D, which are gravity, atmosphere composition, we have oxygen, carbon dioxide, and other gases. Radiation level, MSP per year, temperature range in centigrade, which is a Tmin or Tmax, it's between the Tmin and Tmax, and day length in hours. So a population of n candidates, life forms, is created, each described by 5 evolutionary traits or features, which are going to be stored in X variable, with R, B, O, T, and S, which R is radiation, B bone density, O oxygen efficiency, T temperature, and S stress resilience. Each feature is initialized randomly within biological limits, from 0.5 to 5. Here we can see our objective function, which is the most important part here, and all the explanation before was for this section. The objective function quantifies the survival fitness of each organism on the planet. Each environmental factor interacts with its corresponding feature as follows. So we have 5 main equations with its related weight here, as we can see, for each feature. So we have the radiation survival equation here, then we have the gravitational adaptation equation here, then we have the respiration efficiency equation here, then we have the thermal adaptability equation here, and then we have circadian stress equation here. The result is going to be in the range of 0 to 1, which represents survival probability values close to 1 indicate stronger adaptation. So in the optimization level, at each generation we have evaluating the fitness for all individuals using the objective function of f. Select the better candidate, we are using relative selection traditional way. Crossover, which makes genes of selected pairs to create offsprings. Mutation, which will be applied to small random changes to preserve diversity. And finally, we have the replacement from the next generation and repeat until the maximum number of generation is reached, or the population converts, which here we have number of generations. And output after the evolution would be the best individual, which has those features of R, B, O, T, and S, as I mentioned, radiation, bone density, oxygen level, and more, in the range of 1 to 5. 5 means higher mutated, but it doesn't guarantee the best results. And the best result, which is the higher fitness, is going to be stored in the maximum fitness. Okay, we are in the coding environment of Python, in the Spider. Here we have genetic algorithm, and here we have genetic algorithm for exoplanar adaptation simulation. The genetic algorithm code is work exactly same as Firefly algorithm and differential evolution algorithm in section 3 and 2, which I explained earlier. Also, for the description about this algorithm, please refer to section 1. Here we have the main body of the genetic algorithm. Population size is 50 and generations are 100. Also, we have the same 8 selected functions as before, which are Sphere, Matthias, Rosenbrock, Powell, Rastrigen, Ackley, Eggholder, and Bale from different categories. And finally, we have the plot. When I run the code, we get 2 plots. One of them is function landscape with best solutions found for genetic algorithm on 8 different functions of Sphere. As you can see, the best solution has been found, which is near to the violet area. Also for Matthias, Rosenbrock, Bale, Eggholder, Ackley, and Rastrigen. Also for Powell, because Powell is 4-dimensional, it's not possible to plot it easily, but with a little bit of manipulation, we can do that. Also here, we can see the convergence of each test function solved by genetic algorithm. Okay, we go to the genetic algorithm for exoplanetary adaptation simulation problem. Here we are going to import required libraries. Here we have the planet function, which is called generate planet. We are going to generate parameters for random exoplanetary environment, like the name of the planet, the stars, the gravity, atmosphere, the range of them, the gas, oxygen, carbon dioxide, and other gases, and also radiation level, temperature. and day length, and their lengths. As you can see, there are some range for each parameter. Then we have the fitness function evaluation for the bioorganism. So this one is score a genetic profile based on survivability in given planet condition. Traits or features are radiation resistance, bone density, oxygen efficiency, temperature adaptability, and stress resilience. Also here we have the weights. So we consider 25% for weight for radiation and oxygen, 20% for gravity and temperature, and 10% for the stress resilience. Genetic algorithm parameter consider 500 population size, 1000 generations, and we have 5 features, which are these 5. And mutation is considered 2%, a range for genetic traits or features. Here we have the evolution loop, which we have the evaluating the population fitness, selection, crossover and mutation, and finally the update. Final result, which was a lot of results, and finally the fitness convergence plot. Okay, here in the convergence, because we are looking for fitness, it's going to increase over time, and we can see convergence happened very soon, and with a little fluctuation, it just continued. At right, we can see that the genetic algorithm optimization is completed. So it generated a random planet and random bioorganism. As we can see, planet name, star name, gravity is 1.9, like double size the Earth. Atmosphere composition 7% oxygen and 19% carbon dioxide, and other gases like 23%. Radiation level, we can see 376 MSV per year. Temperature -69 to 1.7 centigrade, so it's very cold environment. Also, the gases are not proper, 23%, just 7% oxygen. The gravity is okay, it's fixable, and day length is just like 10 hours. So also we can see what happened for the best candidate solution here. So as you can see, a lot of mutation happened, and the bioorganism tried to mutate itself to survive in this environment. But at the end, we have the fitness function in the best case scenario 0.3, which is not good enough. So that means survivability of this creature on this planet is very low. So we are going to run one more time. Maybe we achieve a better solution. This time is 0.4. Is not good again. Let's run it one more time. Not good. Okay, this time is better. So we have 0.6. Okay, here we can see the planet name, star name. The gravity is very low, 1/5 of the Earth. Atmosphere composition, we have like 32%, way more oxygen than the first one. Carbon dioxide 36, and 89% other gases, which is not good. So a lot of mutation needed here. As we can see for the second one, around 5 happened. And radiation level is 255 MSV per year, and temperature range of -87 to 62. So basically we have cold and warm environment. Day length is 80 hours, which is good. So basically a little bit of improvement in the day length, in the temperature, in the radiation level, in the atmospheres. That's why it happened. So I'm gonna run it multiple times to see maybe above 0.8. We can achieve above 0.8. Not that good. Not that good. This is good. Horrible. Okay, this time we achieved something like around 0.8, which shows a lot of more oxygen, less carbon dioxide, and we have other gases. The gravity is close to Earth gravity, a little bit heavier. Gravitational force, actually, a little bit more force. Radiation level is lower, and the temperature range is good, like -35 to 48, but day length is 10. Also, we have a lot of mutation, except the first one. So basically, the bioorganism living in this planet has a high chance of survivability and living.